We've been talking about matroids, and we have a lot of results so far built up about matroids. So it's, other than observing that they are a generalization of some definitions or some defining notions on vector spaces or on graphs, it's important to ask, what can we do now that we've developed this machinery? So, algorithmically, we have two main accomplishments so far. One is we've given a characterization of the polytope of various polytopes relating to matroids, independent set, spanning set, base polytope, etc. So that means that we can solve linear programming problems potentially over those. Note that if you look back at the previous lectures, they have exponential size. So it's not yet immediate that we can do that. We need to show that we can solve the separation problem, or perhaps come up with a special purpose algorithm. But we certainly can't just plug it into simplex. But nevertheless, it's an algorithmic tool that we could use. And also the greedy algorithm is our other main fundamental result about matroids. We can use a greedy algorithm to efficiently find maximum weight independent sets. So it's interesting to ask, this greedy algorithm is so great, perhaps we can see if we can apply it to other types of problems that we have studied before. So, for example, a problem we've spent quite a bit of time thinking about is matching, and the easier version of matching is bipartite matching. So let's just explore whether greedy succeeds in finding a maximum weight matching. Maybe we could have skipped all of that work. Of course, the answer is going to be no. But let's see an example of that. So let's take a simple example of a bipartite graph, and I'll make a few edges here, and let me put some weights. I'll change color here. So this first weight is going to be 2, and then the other edges that go right across are going to have weight 0, and then every other edge is going to have weight 1. So we can see that the maximum weight matching, I guess to make it, let me change this a little bit. Let me make this, I might as well make that 3 and everything else 2 except for the zeros. Just to, you'll see in a minute. So what does greedy do in this case? Greedy will select this edge, and then that rules out the 2 other edges that are adjacent to that edge. And so you basically see that the best greedy could do is perhaps take take this. So greedy gets 2 edges and total weight 5. But we know from right, so I'm just checking that I haven't made a mistake. Every other edge is indeed ruled out, but we know that an optimal algorithm would instead, let me choose a different color, take this edge, and this edge. So the optimal algorithm takes 3 edges that have in total weight 6. So greedy in this example is not optimal. And just as an aside, you can see that we have an augmenting path, and this was just checking indeed that everything we said about bipartite matching is still in play in this very simple example. Okay, so the upshot here is that greedy is not is not optimal. So it fails to find a max weight independent set. I'll just put this in quotes since we haven't defined this carefully. And essentially this is telling us that bipartite matching is not a Matroid problem. We need more structure. Right? So it's not, we can't define an independent set, an independent system where the maximum size independent set would be a maximum size matching. That's essentially what this is kind of telling us. At least that's an informal way to think about this little example. On the other hand, bipartite matching can be cast as a problem that has to do with matroids. In particular, it is a matroid intersection problem. So, what do I mean? Bipartite matching is that we have a graph that has two color classes, V1 and V2, and some edges. So this is our familiar picture from our bipartite matching days. This is V1, this is V2, and we have edges from V1 to V2. Now I'm going to define two matroids, and we'll see that their intersection is going to be the set of matchings. And when I mean matroids, I mean I need to define what is the ground set. So any matroid here is I need to define a ground set. Well, the ground set is going to be the set of edges. And I need to define independent sets. And what we just saw in the previous slide, or we saw evidence of, let's say, we have not fully careful there, is that I couldn't say that the set of independent sets, I couldn't call calligraphic I the set of matchings, because you should check for yourselves why this is in fact not the case, but the set of matchings fails one of the two properties. I mean, in fact, even this example shows exactly which it fails. We can't augment the yellow matching using the three-edge matching to get a three-edge matching. We need to do this alternating path, which is not an augmentation the way that the matroid properties guarantee for us. Okay, so we're going to do the following thing. We're going to define two matroids. And I1 is going to be all subsets of the edges such that for any vector on the left, I satisfy that the cardinality of my matching intersect all edges that are incident to that particular vector on the left. So that would be, for example, if this is the little v I choose, it would be delta of v again, it would be those three. This has to be at most one. Certainly any matching can only choose one of those. And then also I2, then you can already guess what this is going to be. I2 is going to be everything where for every vertex in V2 on the right, the set of edges I choose intersect the set of edges that are incident to any particular node on the right also has to be less than 1. So it's easy to check that, or maybe I'll just leave this for you. So as a first exercise, check that MI are both matroids. So MI are indeed matroids. That means you need to check that the independent systems that I've defined satisfy the two properties. And also make sure that you convince yourself that the intersection of I1 and I2 is indeed the set of all matchings. So two things that we've seen. First of all, E with the intersection of I1 and I2 need not be a matroid. So perhaps I should add this as an exercise. to construct a specific example of a bipartite graph where I1 intersection I2 is not a matroid. And then after you've done this first exercise that shows that individually they are matroids, you'll see that the intersection of two matroids is not necessarily a matroid. Another problem that is familiar to us is that of arborescences. So remember this definition. Again, we've seen this many times now in this set of lectures. We have a directed graph D, and we have a vertex set V, and then we have a set of edges. And again, I'll just write it explicitly as this is a subset of V cross V, and they're directed. And a subset of E is an arborescence if it satisfies two properties. First, if I forget about the directionality, there are no cycles. So not just no cycles in the directed graph, but also no cycles in the undirected graph. No cycles in the undirected subgraph with edges T. And then also I need that every vertex has at most one incoming edge in the directed version. So just to clarify this situation, this is an undirected, this is a graph who in the undirected version is has no cycles, so it satisfies property A, but it does not satisfy property B. So this example fails property B. Okay, and we're going to play exactly the same game we did on the previous slide. I'm going to write two matroids, and it's actually, you can probably do this, you can probably see what's going to happen. The first matroid is going to enforce property A. The second matroid is going to enforce property B, and therefore the intersection of the independent sets would give us all arborescences. So M1 is going to be, again, the same ground set with I1. M2 is going to have the ground set of all edges, independent set I2. And what are I1 and I2 going to be? I1 is just going to be the graphic matroid on the undirected graph. So when I say that it is the graphic matroid, I'm abusing notation and terminology a little bit. I mean, it's the independent set that corresponds to the graphic matroid. So it is the graphic matroid on G, so it's an undirected graph, equals VE. So in other words, any element of I1 is just any subset of the edges that have no cycles. A subset of the undirected edges without cycles. In other words, property A. And now, what is I2 going to be? It's going to be what we defined as a partition matroid. And in fact, I should have mentioned this on the previous slide. Perhaps I'll write these. Both of these are partition matroids. So bipartite matching is the intersection of two partition matroids. I2 is also going to be a partition matroid, which is going to be very similar to what we had on the previous slide, except we need to take care of directionality. So it's going to be all subsets of E, where for any vertex in V, the number of edges in the subset intersect with the number of delta minus, because we have a directed graph, incoming edges is no more than 1. So it's easy to check, but I'll just make sure, I'll just leave it as an exercise, that I1 intersect I2 is the set of arborescences. So what this should be starting to suggest for us is that matroids by themselves are powerful, but the intersection of matroids is also very powerful, and it allows me to express many different things. And of course, what's particularly interesting is when I take the intersection of different types of matroids. So now let's just define this properly. If M1 and M2 are matroids, when I say matroid, again, I mean that the independent system satisfies those two properties. And they have the same ground set. Their matroid intersection what we care about is I1 intersect I2. And we've seen that in general, this is not a matroid. This is... And when we say that we want to study this intersection, I1 and I2, what we're saying is that basically we want to understand things like questions like what is the max size of a set in I1 and I2? And the algorithmic version, how do we find this? And then the polyhedral question. What is the polytope of the matroid intersection? Again, what that means is, what is a characterization in terms of inequalities of the convex hull of the indicator function of every element of this intersection? So we're going to get to all of these questions, but for starters, we'll focus on this first property, on this first question. What is the maximum size of any set in the intersection of I1 and I2? I've called this a main result. It's a main result of this lecture and the next lecture. So here's what it says. Again, I have my M1 and M2 on the same ground set. These are matroids. And with rank functions R1, which sometimes I'll denote by RM1 and R2, respectively. The result says that the maximum size of a set in the intersection of I1 and I2 has a variational characterization as a minimization problem. This is something that we should be expecting at this point. When we know we have a polyhedral characterization, we can smell some kind of duality result is coming. In fact, we're not going to give a duality-based proof for this in the next lecture, but there is a duality-based proof. So the theorem says the following: the maximum over all I in the intersection of I1 and I2 of the cardinality of I is equal to the minimum over all subsets U of the ground set E of R M1 of U plus R M2 of the complement of U. We're going to prove this in the next lecture, but before we do that, I want to turn to a few immediate corollaries that we can obtain from this. Okay, so first corollary says the following. So again, mi are as in the theorem above. And assume further that the number of independent elements, the size of a base in M1, is equal to the size of a base in M2. Again, this is an assumption. This is not necessarily true for any two matroids on the same set. And you should think about an example where they're not the same. Then the two matroids have a common base if and only if R1 of U plus R2 of the complement of U is at least equal to R1 of E, which is, as we said, is equal to R2 of E for every U in E. So in other words, when do two independent systems already have a base in them? It's when this holds. And the proof is really immediate, so I'll leave it as an exercise. Let's flip back to see the theorem, and so we can kind of think about it for just a second online to see why this is true. So this theorem is telling me that the size of a maximum set in the intersection of independent sets is equal to this minimization. So you can use that to conclude this. Okay, now it's interesting not only to ask for the maximum size of an independent set, but another notion that's important is the minimum size of a set that spans. These can be different. So if I have one matroid, then the minimum size of a set that spans is by definition the same as the maximum size of an independent set. Again, such things are immediate from linear algebra. But of course that this need not be the case if we have the intersection. So let's write this corollary, this characterization. So again, for matroids M1 and M2 as above, the minimum size of a common spanning set. So no, I'm not asking for this to be in I1 and I2. In general, unless I1 and I2 have a common base, as in the previous corollary, unless that's the case, then a minimum size spanning set will have more elements than a base, and in particular will not be in the intersection of I1 and I2. So the minimum size of a common spanning set is, so in other words, I'll write this as again in the same way that I wrote the other one, min cardinality of S such that S spans M1 and spans M2. So again, might have to be bigger than a base, is equal to, again, we see a min-max relationship here. It's the maximum over all subsets U of the ground set of R1 of the ground set, the size of the biggest base in Matroid 1, minus R1 of U, plus R2 of E, the size of a base in Matroid 2, minus R2 of E minus U. So let's see why this is the case. Well, if S spans M1, it has to contain some base of M1, and if S spans M2, it has to contain a base of M2. And as soon as S contains a base of M1 and a base of M2, there's no reason to put anything else. So immediately we see, let's just say, so S must contain a base of M1 and a base of M2. So we can immediately write down that S, the cardinality of S, or the best S, maybe I should put an S star here. Don't want there to, we're not talking about duality, so hopefully this won't confuse us. The best S, the S that achieves the minimum over here, the cardinality of that is the minimum over all B1, B2, where, I won't write this out, where B1 is a base for M1, B2 is a base for M2, of the union of B1 and B2. Again, if you have a common base, you just take this to be the same element. And this is equal to, again, this, I'm just writing out what the cardinality is of the union. It's equal to the cardinality of one plus the cardinality of the other minus the cardinality of the intersection. So this is a minimum of B1, B2 of cardinality of B1 plus cardinality of B2. You can see now I've already found the first two of the four terms on the right here, in particular the ones that are not subject to the maximization, minus B1 intersect B2. And I can just pass the max inside now. So this is equal to B1 plus B2 minus, and because I'm passing the min through the minus sign, this now becomes a max over all B1 and B2 that are bases for B1 and B2. B1 intersect B2. But what is what is this? This is exactly the maximum cardinality of any set in the intersection of I1 and I2. So this is the quantity that's given by the theorem. And you'll recognize these two, those two terms. And so that's how this follows. So that concludes this corollary. In the next lecture, we are going to give a proof of this Matroid intersection theorem. So we will pick it up then.